Hello friends, we are going to discuss the transient or unsteady state of heat flow. See, this lecture is introduction to transient and unsteady state heat conduction with an emphasis on lump system approach. The equation that models a lump system was derived, and some more example will be done. And the Biot number was introduced as a criteria for the applicability of lump system approach. So this chapter we will be discussing in between conduction and convection. So in conduction and in transient approach, what is the difference? In conduction we are following Fourier's law. Q is equal to minus Ka into dt by dx, and our general equation is minus del t by del x into K into dt by del x plus del t by del y into minus K into del upon del z minus K into del t upon del z plus में Q dot generation inside the body is equal to del T by rho C into del T by del T. So this part is showing transient part, and this is the heat generation within the body. So this is the cubic element. So whatever heat is flowing Q1 and whatever heat is flowing from this phase is Q2, and net heat stored in this body is Q dot generation inside the body. So in steady state, del T upon del T will be equal to 0. So if you are measuring the temperature of this point 1, 2, 3 inside a body, then if I am writing temperature versus time graph, suppose this is at temperature Ti, so 4.1, this temperature is not going to change with respect to time. This is steady state. And 4.2, suppose this is the temperature, then this is not going to change. Suppose 0.3, this is the temperature, it is not going to change. So in your plane wall question, when you draw this for different point inside the plane wall, this is temperature and it is with respect to x. So if it is 100 degrees Celsius air and this is 50, so this temperature is going to vary. Del T by del x will not be equal to 0, but del T by del T equal to 0. Means if you have seen this location at t equal to 5 second, at t equal to 10 second, at t equal to 20 second, this graph will be going to look like this at different interval of time. So this is your normal conduction problems in chapter 1. But in transient heat flow, The same body, if you will take 1, 2, 3. So if you are measuring the temperature of these points at a different interval of time, now in transient state, del T by del T is not equal to 0. So it means temperature is going to change with time. Suppose at T equal to 0, all these points are at the same temperature, that is T equal to 100. So after some time, when the body will start getting cooled down, its graph will follow like this in transient state. So it is showing at a particular instant of time. Suppose at T equal to 0, T is 100. So this is the case. Suppose you will show different sectors. So this is 100, this is 100, this is 100. Now T equal to 5 seconds, T is equal to 80 degrees Celsius. So this is the whole body. Then the whole body will be at a temperature of 80 degrees Celsius. So the temperature is not going to change with respect to spatial distribution. So temperature is not going to change with respect to x, y, z is equal to 0. Temperature is not a function of x, y, z. Temperature is a function of time only. So at T equal to 5 seconds, at T equal to 10 seconds, T equal to 0 second, and that time is started. So this is the basic difference between our conduction and transient heat flow. Now if you will consider a small body, whose mass is m, density rho, volume v, heat capacity is C. We will derive the expression for transient heat flow. And you have some fluid that is at a temperature of T infinity, and its temperature is T at some interval of time T. So what will happen? Heat will flow into the body Q dot. Due to this heat flow, the body will gain some internal energy. Okay, so the heat lost by the fluid is equal to heat gain by the body during time dt. So how much heat it will lose? H into this body surface area is As into T infinity minus T dt. This is the heat flow during time dt. Because this is in watt, so it is joule per second. So into time it is in joule. So how much heat has flown into the body is m c d of T minus T infinity. So this much heat it has flown into this body. So if you will rearrange this expression, dt of HAS upon rho V. Mass we can write rho V into Cp, heat capacity of the body, then 1 upon T minus T infinity into d of T minus T infinity, integrating with respect to 0 to some interval of time T. Suppose its initial temperature is 50 degrees Celsius, then how much time it will take to reach 80 degrees Celsius if the fluid is at 100 degrees Celsius. So this is temperature T final. If I will write this expression will come ln of T final minus T infinity upon Ti minus T infinity is equal to e raised to power minus Ha upon rho V Cp into tau. So this is called time constant, not this one, this is the time. So if you will draw the graph, so this graph is so if you will draw the graph between Ti and T final with respect to time, and this is exponential in nature. So this graph is slope is decreasing from 90 to 0. So what it means that dt by d tau or dt with respect to time, body will gain heat at a faster rate during initial period of time as compared to the same heat flow during the later period. So the temperature rise of the body will be less as compared to the temperature rise of the body during the initial state. So if we will consider this vector as B,